Hey everyone, so today we're going to work on notes about continuity. So the first thing we want to get a handle of is what is the definition of continuous in calculus. So continuous means that at some value x, the limit exists and it is the same as the function value. Okay, so here's what that would look like. Basically, it's somewhere you don't have to pick up your pen. It kind of is that smooth curve, so I'll show you. If you had something like this, and let's say this was point C right here. Okay, you would have both the limit exists, so the limit as we approach C, that exists, and also whatever this f of C is, whatever this y value is the same as the limit. Okay, so we'll talk about kind of what is a discontinuity, and I think I've mentioned it before, and so yeah, we're going to look at those below. So to figure out if something is continuous, often you're going to have to justify these within an AP problem in a free response format. So you're going to have 3 steps every single time, unless one does not exist. So first you're going to evaluate the function at that value. Then you're going to evaluate the limit. You need one-sided limits. So from the right and from the left, just as a heads up, if it is a graph. And finally, we have to determine if the limit as x approaches C is the same as the function value. So basically step 3 will be, are these the same? Okay. If any step does not exist, then the function is not continuous. So for example, if you go to find f of C and this is undefined, then we can just stop. We don't even have to continue on. Same thing with the limit. If the limit does not exist, then this problem's done, and it is not continuous because the limit does not exist. Okay, so let's take a look at this graph right here. Okay, we'll do a couple examples. So how about at x equals 1, what's happening here? Well, at x equals 1, if we went through kind of our 3 steps, x equals 1, hopefully you guys notice, you'd have to pick up your pencil to get to the next point. Maybe from afar you can see that limit is different, but if you were going through those steps, basically here's what you would do. You would first say, what's f of 1? F of 1 is 1. You would now do f of 2, not f of 2, sorry, step 2, which is finding the limit. And so you would do the limit as x approaches 1 from the left. As x approaches 1 from the left, we approach 0. And the limit as we approach 1 from the right, we approach 1. Okay, so we already know right now that this is not continuous because, remember, if one of the steps does not exist, right? So if this didn't exist, or in this case, the limit as x approaches 1 does not exist, okay, then it is not continuous at 1. Okay, and we're going to talk about these in a second. This is called a jump discontinuity, where we have to pick up that pencil and continue our graph, and the limit does not exist. Okay, for one more value I wanted to talk about is x equals 2. What's going on here? Well, x equals 2 looks a little strange. There's something going on there. Okay, we have an open circle. So let's figure out what's going on at x equals 2. If I start out with my first step, which is what is f of 2? F of 2 is 2, where that closed circle is. My second step is the limit as x approaches 2 from the left and the right. Okay, so from the left, I'm approaching 1. From the right, I'm also approaching 1. So the good news here is that the limit as x approaches 2 exists, and it's equal to 1. Okay, now notice, this one though is going to fail that third step. Remember, the third step said determine if they are equal. So step 3, is f of 2 equal to the limit as x approaches 2 of f of x? No, right? Because this was equal to 1, this was equal to 2, so therefore it's not continuous. Okay, so we're going to do these a little more formally below, but I just wanted to give you a heads up as to what type of problems you're going to see. So we're going to use this new graph here. That was kind of your brief examples, and now we're going to use kind of a more extensive graph. remember you have 3 steps. So again, if you need to look at those 3 steps, this is what you're going to need for that AP free response. So evaluate the value, evaluate the limit, determine if they're the same. Okay, so, and again, you do need those one-sided limits. So let's take a look at letter A. What's happening at -2? Okay, hopefully right away, you guys could tell me yes or no. So if I said determine if f of x is continuous at -2, what do you guys think? Well, hopefully you say no, because we do not continue here. We have this whole break right now, and the limit's going to be, the limit is not going to exist because from the left and right, we're approaching different values. So that's really where you can start with this. You can show step 1 if you'd like. What's f of -2? That is equal to 3. But take a look at step 2. As I find those limits, -2 from the left, that would be equal to 3. And -2 from the right, that is equal to 1. Okay, so remember that little post-it up there. It said if any of these steps don't exist, then we know it's not continuous. So we don't even have to go to step 3, and because really at this point we see that the limit as x approaches -2 of f of x does not exist, which means one of our steps doesn't exist. Therefore, if we're going to justify here, we showed our work and we said f of x is not continuous at x equals -2 since the limit didn't exist. Okay, so there's your justification. Again, we start those steps. If any doesn't exist, we're done. Or we get all the way to step 3 and we see that it does exist, or they're not equal. Then it does not exist. It depends. So let's take a look at letter B. Okay, again, pause if you need to. Letter B is talking about x equals 4. So what do you guys think? Take a look at 4. Think in your mind right now, is this continuous? Is f of x continuous at 4? Excuse me, not -4. Okay, well, hopefully you're thinking yes. Okay, so let's prove it. We have to justify still. So step 1, what is f of 4? F of 4 is 2. Step 2, what's our limit? So I approach 4 from the left. I'm going towards 2. As I approach 4 from the right, I'm approaching 2. Therefore, the limit as x approaches 4 in general is 2. Okay, and then hopefully what you guys are thinking is that step 3, we're finally there. Step 3 is wondering if f of 4 is equal to the limit. And hopefully you guys are thinking, yes, we have f of 4 equals 2, the limit is equal to 2. Okay, so you would answer this by saying f of x is continuous. Since f of 4 was equal to the limit as x approaches 4 of f of x. And you could even say both of those things were equal to 2. Okay, so let's try one more here at x equals 5. And again, I want you to take a look at 5. I'll switch to orange here. Take a look at 5 and decide for yourself right now, do you think it's continuous at x equals 5? Okay, hopefully you're thinking, no, it's not going to be continuous. So let's prove it. All right, step 1. What is f of 5? F of 5 is -4. Okay, so that existed, so good news, we move on. Step 2 is what is the limit as we approach 5 from the left? And the limit as we approach 5 from the right. Again, guys, for that free response problem, if this is to be on the AP test, you do usually get a point for showing these one-sided limits. So definitely make sure we're doing that. It is required for this justification. And in this case, we look at 5 and from both ways, we're approaching that value of negative 2. So therefore the limit as x approaches 5 is negative 2. Okay, but you guys probably already said, and hopefully we discovered, this is not continuous. Why? It's going to fail step 3, which says, is f of 5 equal to the limit as x approaches 5 of f of x? In this case, they're not equal, right? This was negative 4, this was negative 2. Okay, so it's not continuous at x equals 5. Not continuous since f of 5 is not equal to the limit as x approaches 5. Okay, so those are pretty much your standard 3-step situation, guys. I want to talk briefly about the types of discontinuity because you've seen different versions, right? You've seen kind of that hole in the graph. Sometimes there's a jump. In this picture above, we didn't work on a vertical asymptote, but that also comes up as a discontinuity. So take a look at the next page when you're ready. And we're going to talk about the 3 types already kind of written out for you here. So a point of discontinuity. Okay, points of discontinuity we also call a hole in the graph, if you hear me say that. Think of it as a point that's been removed. And just as a heads up, we also call this sometimes it's one of the removable discontinuities. Okay, example, this is at negative 2. So notice here, there's a hole in the graph. But the limit existed, right? So there's a limit, but there's no value there, or the value does not match the limit. And same thing here at 6. At 6, the limit exists. We get really close to this point, but it's not the same as the function value. Now, there's kind of 2 situations here, right? It says, what step do we fail for the point of discontinuity? Pretty much we fail step 3 overall, because really what's happening is that f of a is not the same as the limit. Now, if you look at these 2 things here, I would say at negative 2, we actually fail step 1. Because if I asked you what's f of negative 2, f of negative 2 doesn't exist. So that fails step 1. How about over here? You see this tiny point, so that one exists. If I said what's f of 6, you would say it's 7, but the limit as x approaches 6 from both sides here, typically we'd write one-sided for the sake of example. I'm just going to ruin it. That's equal to 1. So since they both exist, but they weren't equal, we have a hole in the graph. Okay, so, and it might fail step 1. Right here, we don't even have a function value, so that is another way we might have a hole in the graph. Okay, so that is a point of discontinuity or a hole in the graph. Let's take a look at a jump discontinuity. A jump is, again, think of your pencil having to jump the paper. So if I was going towards negative 3 and I had to pick up my pencil and jump to continue, okay, that is a jump discontinuity. So example at negative 3 and at 4. Coming this way, coming this way, coming this way, jump, pick up your pencil, continue the graph. Okay, so this is called a non-removable discontinuity, as a heads up. Okay, remember, point of discontinuity was removable. And then what step does this fail? Well, the biggest issue here, guys, is that we don't have a limit existing, right? The limit from the left and right is different. So this fails step 2, which is the limit as x approaches a of f of x. It equals, it doesn't exist. So in a general sense, you could say, the right hand and left hand limits don't exist. Excuse me, the left hand and right hand limits are not equal. Sorry about that. Okay, so again, that's a jump. And think truly it's like as though you were on a roller coaster here and then it suddenly fell to this next level. That's a jump discontinuity. Okay, infinite discontinuity is the last type here, guys. And infinite discontinuity is that vertical asymptote. Okay, so infinite discontinuity, it's non-removable as well. So notice jump and infinite are both non-removable. This would be like at x equals 3. So I don't know if you guys can see this dashed line here at x equals 3. Technically, to draw this graph, if I was drawing from the left, I'm going this way. There's really no way I'm going to get back unless I pick up my pencil and restart up here. So again, it's that picking up your pencil helps you with figuring out if something is continuous. So what does this one fail? Well, this really just fails step 1. Because if I said, what is f of 3 in this picture, right? F of 3, that would be undefined or does not, there's no function value here. So that's what it's failing. Okay, we're gonna look at one more problem here, okay, and then we'll save the making functions continuous for class. So take a look here at problems A and B. We're just gonna finish this up. Now notice we don't have a graph, okay, but we do have this piecewise function. So we have a lot of info, but we don't have that visual. So we will have to do some plugging in and figuring out what's going on. Okay, so is f of x continuous at 2? Justify, okay, justify, that's that 3-step situation, okay, that we've been talking about. So let's take a look here. Okay, the first step, what's f of 2? F of 2, here is where it's equal to 2, so 2 minus 4, absolute value, that would give me 2. Okay, so that exists. How about step 2? What happens as I approach 2 from the left? What happens as I approach 2 from the right? Okay, so from the left, guys, notice this is our function that's coming from the left because it's at like 1, 0, -1, it's approaching 2, but it's only when x is less than 2. So 2 squared plus 2, which is 6. And then from the right, well, that would be this guy, right? Because between 2 and 7, I'm at 2 minus 4, which is 2. Okay. Well, if I ask you overall, what's happening as we approach 2? What's the limit as we approach 2? You would say it does not exist because 6 and 2 do not match. Think of what that looks like, guys. From the left, I approach this value of 6. From the right, I approach this value of 2. Okay? I want you to think what type of discontinuity this is. All right? Hopefully you're thinking jump, right? Because the limit didn't exist, left and right were different, and we had a function value. So just to finish up here, okay, we're going to say that f of x is not continuous since the limit as x approaches 2 of f of x does not exist. Okay, and then notice in this problem it said, okay, well, if it's not continuous, what type of discontinuity exists? And again, I mentioned this to you guys, this is going to be a jump discontinuity. And remember the other word, or it might be also considered, this is a non-removable discontinuity. The only removable one is the point of discontinuity. Okay, and we know it's a jump discontinuity. Why? Well, the biggest giveaway is this. Left-hand and right-hand limits were different, but a function value did exist. So that kind of helped us with figuring out it was a jump. Okay, and then the last one here, how about at x equals 7? Well, let's take a look at what's happening at 7. We have a value at 7. Notice it says when x is 7, it's just 5. So what's f of 7? 5, no debate there. Okay, but then from the left and right, we have to figure out what is happening with those limits. So take a look, what happens as we approach 7 from the left? Okay, that's going to be this guy right here. So 7, where am I at? -4, which is 3. The limit as I approach 7 from the right, that would be this function here. 7 minus 4, which is 3. Okay. Well, this is good news because now we know the limit as I approach 7 in general is 3. Okay, so think about what's happening here, guys. What's going to happen with step 3? Step 3 is asking again, is f of 7 equal to the limit as I approach 7? Hopefully you notice here we've got 3, we've got 5. Answer here is no. So it is not continuous. But the fact that the limit exists, right? The limit exists. We approach this value of 3, and then we had a value of 5. Okay, what type of discontinuity is this going to be? It's going to be a point of discontinuity. Okay, so take a look here. The final answer is just we want to say it's not continuous And that was because it failed step 3, since f of 7 is not equal to the limit as we approach 7. Okay, and the last thing here just says, what type of discontinuity would it be? We just kind of discussed this. This would be a point of discontinuity. Because the limit existed, but it just wasn't equal to the function value. So it was a hole in the graph with a darkened circle somewhere else. And again, this is called a removable discontinuity in case that comes up. Okay, so I have one more example down here for you. We're going to work on this in class, as well as making functions continuous. So this is important here. This is going to be when values are not available, such as a and x. We're going to find out what's a value for a that would make this function continuous. And then down here, I just wanted to show you guys, we don't have to actually take any notes here. This is just simply giving you kind of a shortcut to how do we know which type of discontinuity it is, what are they called, stuff like that. So just wanted to have that there for you. Besides that, thanks for watching, and please bring in any questions.